better understand the relationship between the structure and the behavior of dynamic systems, we'll look at two examples: fish catch decline and flu epidemics. In both of these examples, we will start with the behavior of the system and then infer the structure of the system from its behavior. Let's start with fish catch decline, which is a global problem. This graph shows the total fish catch for Mozambique over the period of 60 years. From 1950 to 1980, the total fish catch grew exponentially. Then, between 1980 and 1990, the total fish catch peaked and began to decline from 1990 onwards. Other trends that can be observed over the last 60 years are a steady rise in the human population and a steady decline in the amount of fish habitat, such as coral reefs, seagrass, and mangrove forests. Let's now put these three trends onto one graph and analyze the expected future trends. Looking at the total fish catch and fish habitat, we might expect these to continue to decline in the future, but at a slower rate. For population, we might expect this to increase in the future, but also at a slower rate. If we look across the past and expected future trend for the total fish catch, it exhibits overshoot and collapse behavior. Using the principles that link system behavior to system structure, what are the feedback loops responsible for this overshoot and collapse behavior? The generic structure of an overshoot and collapse system contains one reinforcing loop and two balancing loops. The reinforcing loop is responsible for the rapid initial growth in the state of the system. As the state of the system approaches carrying capacity, the first balancing loop slows growth in the state of the system. As the state of the system is still increasing, the second balancing loop begins to erode carrying capacity, which results in the state of the system collapsing to a new, but lower carrying capacity. Let's now look at each of these feedback loops in relation to our fish catch decline example. Here, the state of the system is the total fish catch. This initially grows exponentially, which is explained by this reinforcing feedback loop. Here, as the human population increases, the net growth in fish catch increases because we have an increased demand for fish. This in turn increases the total fish catch. The increased total fish catch allows the population to increase even further, which increases the net growth in fish catch again. As a result, both the population and the total fish catch grow. However, after growing rapidly, the total fish catch growth begins to slow. Why does this occur? It's because of the balancing loop B1. As the total fish catch grows, the fish recruitment, that is, the production of baby fish, begins to decline, given that there are fewer adult fish in the population. This acts to reduce the net growth in fish catch, which in turn slows the growth in the total fish catch. This balancing loop B1 explains why the total fish catch growth slows over time. The final part is the collapse in fish catch, which is triggered by a second balancing loop, B2. As the total fish catch continues to grow, the fish habitat degradation increases. This reduces the fish habitat carrying capacity, which further reduces fish recruitment, which further reduces the net growth in fish catch, leading to a collapse in the total fish catch. This balancing loop B2 explains why fish catch declines over time. Let's now summarize the fish catch decline example, referring to the four levels of systems thinking. The system structure is rising population, leading to overfishing and damage of fish habitat, which in turn leads to a decline in fish catch. This system structure creates the observable patterns of rising population, a rise then decline in fish catch, and a decline in fish habitat. The emergent event or outcome of these patterns is a fish shortage caused by human population growth and declining fish catch. Once you can explain the system structure driving the system behavior, you can use it to identify intervention points, which are points that can be changed in order to influence the behavior of the system. So what could be the possible intervention points in our fish catch decline example? To start with, how can we manage the total fish catch? We might introduce alternative livelihoods to reduce the dependence on fishing. Then, how can we reduce the fish habitat degradation? We could use less destructive fishing techniques. How can we increase the fish habitat carrying capacity? We could restore and protect our fish habitat better using marine protected areas. How can we improve the fish recruitment? We might implement fish restocking programs through fish nurseries. And finally, how can we control the human population? We might implement population growth management policies.
Now that you understand the dynamics in the fish catch decline example, let's have a look at another example assessing flu epidemics. Out of the common modes of system behavior, which one would best represent the number of people with the flu over the flu season? Before you decide, let's have a closer look at what happens during the flu season. At the beginning of the flu season, the number of people with the flu is small. As the flu season progresses, the number of people with the flu grows rapidly and then peaks. Towards the end of the flu season, the number of people with the flu collapses and the flu season ends. This means that a flu epidemic displays overshoot and collapse behavior. Even without data, we can still establish the feedback loops controlling this behavior. What causes the initial rapid growth in the number of people with the flu at the beginning of the flu season? It's a reinforcing loop. In this example, the state of the system is the infected population, that is, the number of people with the flu. As the infected population grows, the infection rate, that is, the number of people catching the flu, increases. As the infection rate increases, the infected population grows, forming reinforcing loop R1. As the flu season progresses, what causes the growth in the number of people with the flu to slow? It's a balancing loop. As the infected population grows, the susceptible population, that is, the number of people that haven't caught the flu yet, decreases. As the susceptible population decreases, this reduces the infection rate, which slows growth in the infected population, forming the balancing loop B1. Finally, towards the end of the flu season, what causes the number of people with the flu to collapse? It's a second balancing loop. As the infected population continues to grow, after a delay, the recovered or dead population increases. This is the number of people who have recovered from the flu and are immune or who have died from the flu. As the recovered or dead population increases, this further reduces the susceptible population, which further reduces the infection rate and leads to a collapse in the infected population, forming the balancing loop B2. Now that we know the basic feedback loops controlling flu epidemics, we can add detail to these loops. The following causal loop diagram represents the same feedback loops controlling the growth and collapse of the flu over the flu season with more detail. Here, the total infected population has been split into two groups: the infected population without symptoms and the infected population with symptoms. Loop R1 is the same as the reinforcing loop R1 in our simple causal loop diagram. This loop acts to rapidly grow the infected population at the beginning of the flu season. Loop B1 is the same as the balancing loop B1 in our simple causal loop diagram. This loop acts to slow growth in the infected population as the flu season progresses. Finally, loop B4 is the same as the balancing loop B2 in our simple causal loop diagram. This loop acts to collapse the infected population towards the end of the flu season. Now that we have a more detailed description of the feedback loops controlling flu epidemics, we can identify interventions that might reduce the number of people that catch the flu. The first intervention is to keep sick people away from healthy people. This intervention tries to reduce the number of contacts an infected person has with other people per day. By reducing these contacts, this intervention slows reinforcing loop R1 and reduces the number of susceptible people that become infected. The second intervention is immunization and hygiene. This includes immunizing people against the flu and regular hand washing to prevent the spread of the flu virus. This intervention tries to reduce the disease transfer probability if an infected person comes in contact with a susceptible person. By reducing the disease transfer probability, this intervention slows reinforcing loop R1 and reduces the number of susceptible people that become infected. To summarize the steps involved, first, identify a behavior you are interested in. Identify the fundamental patterns, such as exponential growth, goal-seeking, and oscillation. Then, draw the basic feedback loops that are responsible for each part of the behavior. And finally, identify intervention points within the system that can be used to control system behavior. Now that you have seen examples of how the structure of a system can be inferred from its behavior, see if you can develop your own examples.